So number 15 here is just a straightforward application of adding or operations with complex numbers. So we have two complex numbers, z and w, and we do various operations here. So the first one is we're just going to add them. If you recall, the way you add complex numbers is you just add the real components and add the imaginary components. So I'm going to go ahead and do that here for a. I'm just going to go ahead and write the real part under the real part and the imaginary part under the imaginary part. It's easier to keep track of. -1 plus 3 is 2, and 2i plus 1i is 3i. So this would be z plus w. W minus z, we're going to start with 3 plus I, and then we're going to subtract -1 plus 2i. And just like in the rules of algebra, you have to remember to distribute. The operations work very similar to expressions with, say, like x and y. So since we're subtracting, we're going to distribute that negative sign to each of those pieces there. So 3 plus I minus a -1 is +1, and minus 2i is just minus 2i. Now we're going to combine like terms. So the 3 will combine with the 1. Those are the real pieces. That's 4. And then I will combine with minus 2i to get minus I. And that is w minus z. Z times w. The key thing here is to remember you have to do a FOIL type operation here because we have like two little binomials here that we're multiplying with each other. So the first piece will do the first, so that's -1 times 3. The outer is -1 times I. The inner is 2i times 3, and then the outer is plus 2i squared. And now we have to do a little simplification here. This is -3 minus I plus 6i, and then we also have to simplify this I squared because remember, a real piece needs or a complex number needs a real piece and an imaginary piece, but that only includes one I. Well, the key idea here is that I squared is -1, so we can turn that 2i squared into a real number. And now we'll just combine like terms. So -3 minus 2 is -5. Minus I plus 6i is positive 5i. And that would be z times w. And then the last one here, -3w. -3 times the complex number 3 plus I. That's pretty straightforward. We're just going to distribute that -3 to get -9 minus 3i. And I just noticed my answer key had an error on A here. The answer here is correct. I had accidentally had a -2 on the answer key. 16, just another set of some complex number operations. So the first one here is we have the complex number w squared. W is -5i. We'll go ahead and square that. Remember, the square, just like any operation, needs to apply to everything here. So -5 squared, and then the square would also apply to the I, so we have I squared. -5 squared is 25. I squared is -1, and that simplifies all out to -25. Z plus 2w, so z is -1 minus 3i, plus 2 times the complex number -5i. We'll distribute that first. -1 minus 3i minus 10i. Then we'll just combine those remaining like terms to get -1 real part minus 13i imaginary parts. Let's answer to B. Z times w is -1 minus 3i. W is -5i. Well, this is not a this is just a single term times the binomial, so we're just going to distribute that this way here. So we have -1 times -5i minus 3i times 5i. Negative 1 times negative 5i is simply 5i. Negative 3i times negative 5i is positive 15i squared. But then we need to turn, that's actually a real number, we need to get rid of that by substituting I squared equals negative 1 into there. And we get 5i minus 15. And if we write that in the standard way of the real term first, we get negative 15 plus 5i. Then negative z, you can think of that as just the opposite of z. So one way to do that is if z is negative 1 minus 3i, the opposite of z, we can just change these signs on both pieces to 1 plus 3i. Or another way to think of that is negative z is negative of negative 1 minus 3i. If you want to think about putting that imaginary 1 there, we could distribute a minus 1 to each of these pieces. So we get minus 1 times minus 1 minus 3i times minus 1. And that will equal 1 plus 3i. So either way you can think of that, but just don't get tricked by that. That just means the opposite of z, which means change both pieces, the sign of both pieces of the complex number. Okay, so the conjugate of a complex number, pretty straightforward. All you do is change the sign of the imaginary piece. So change of imaginary piece only. So if we have a generic complex number a plus bi, the conjugate, which we will denote with a bar over the top, is going to be the same real piece, but just change the sign of whatever the coefficient of the imaginary piece is. Absolute value, the easiest way to visualize this is the distance from 0 if we plot the number. So like, for example, if we have the number, the complex number 1 plus 2i, we can plot that in the complex plane. Remember, this is the real axis, this is the imaginary, 1 over 2 up. And so this is the complex, the absolute value is that distance right there. And so you have to think about making a little triangle. I made that a little bit small here because I'll draw the triangle out here. That was 1 unit, 1 real unit this way, 2 imaginary units up. And so the way to get that side is just to take the square root of 1 squared plus 2 squared, which is, that's just using Pythagorean theorem here, square root of 5. If you really like to use formulas, you can always remember the absolute value of z. Again, if z is a plus bi, if you actually draw the triangle here, you'll get a, one side is a and one side is b. So the Pythagorean theorem would be that the absolute value is the square root of a squared plus b squared. One thing to make sure to remember, though, is that it's not the square root of a squared plus bi squared. It's not that. Remember, we're thinking about distances here, so the distance is just that real number b. So make sure not to put the I when you're doing absolute value. It's just, I made a triangle with sides a and b and the distance there. So 18, find the conjugates of the following complex numbers. Pretty straightforward. We're just going to change the imaginary piece. 3 is the real, 2 is the imaginary, or negative 2i is the imaginary piece. So we're just going to go ahead and change the sign of that piece there. So there's the conjugate. Same thing here. The real piece stays the same. Change the sign of the imaginary piece. Here, make sure you can think of this as 0 minus 2i. So the real piece of 0 is going to stay the same, but we are going to change the sign of the imaginary piece. So positive 2i is the conjugate. Here, this is just the real number root 2. So we can think of that as root 2 plus 0i, because there's no imaginary component. And then if we change the sign of the 0, well, plus 0 minus 0 is the same thing. So we can just kind of keep that as the same real piece. It's kind of a long way of having the answer not change at all, but it's because there's no imaginary piece. There's no sign to change.